So let's start with convergence of the relevant series. So first of all, we start with, the most basic one is summation 1 by n to the power s. So this converges for s bigger than 1. It's actually converges absolutely. Anyway, the terms are positive, so it is of course absolutely for s bigger than 1. And in fact, the convergence is uniform for s bigger than 1 plus delta. If you take anything more than 1 plus delta, on that 1 plus delta, so on 1 plus delta to infinity, it converges uniformly. So this we know very well, right? So there is nothing mysterious about it. So as a simple, I'll come back to this. We can say a bit more about as s goes to 1, this blows up. That corresponds to the fact that summation 1 by n diverges. But how does it blow up as it goes close to s? Maybe we analyze that right away. So what happens as s goes down to 1? This blows up. In the following precise way. Meaning that, so this is what we call zeta of s, right? So maybe I will, so Riemann zeta function. So zeta of s is actually like, well, in fact, it is 1 over, so this wiggle means ratio goes to 1, but we can be more precise. Zeta of s is actually like 1 over s minus 1 plus, let's write something, zeta tilde of s, where zeta tilde is something that converges on 0 to infinity. So it remains, in particular, it remains bounded as s goes down to 1. Okay, at s equal to 1, it is well defined. Okay, I should have said this before, that because of the uniform convergence on 1 plus delta infinity, this is a continuous function of s, right? So this is a continuous function of s. On 1 to infinity. Now, the thing is, as s goes down to 1, so we can, this is the part that blows up. The part that blows up is 1 over s minus 1. And if you remove that, you get something that does not blow up. So this is the precise understanding. Okay, so maybe I just prove this. So this is not difficult. So why? Let's prove this statement. It's very simple. So zeta of s is summation 1 by n to the power s. Right? And what is 1 over s minus 1? One of the ways in which you prove this is to use the integral approximation, right? So if you may remember, one way to do this is to consider 1 by x to the s integral, which you can do explicitly, and that converges if s is bigger than 1. And from the comparison of the sum to integral, you can do this. In fact, 1 over s minus 1 is precisely that integral. So this is the, so what is it? So from 1 to infinity, we have 1 by x to the s. And then we have this summation 1 by n to the s. If you want, that's often written like this. So it is this area versus the area under the curve. So that's what we are comparing. Anyway, there is no need for the picture. Zeta s minus 1 over s minus 1 will be the sum n equals 1 through infinity 1 by n to the s minus this integral from n to n plus 1, which let's write it like this, dx from n to n plus 1. Because the length is 1 by n to the s integrated will give 1 by n to the s, and this will give the corresponding part of the integral. Okay. So this is okay. 1 second. X to the s minus s plus 1. Yeah, this is correct. So now the point is this nth term. Okay, in absolute value is less than equal to. I mean, anyway, it is positive actually. I don't need to write absolute value. Nth term, it's positive actually. Is bounded by n to the n plus 1. How small is 1 by n to the s minus 1 by x to the s? Right. I mean, so 1 by n to the s minus 1 by x to the s. You can always use mean value theorem. It is the you are taking t to the minus s, right? So it is what is its derivative? Is minus s t to the minus s minus 1. Right. So it is equal to s. Yeah. So it is equal to. What did I want to do? Yeah. So it is equal to s over t to the s plus 1 times x minus n for some t between x and n. So I have just used mean value theorem that this difference divided by the difference x minus n, because I have flipped the sign, this minus goes away. So is the derivative at some interior point between n and x, which is actually s minus s over t to the s plus 1. Okay, so this is what we have. And that is anyway going to be bounded by, that is after all smaller than x minus s, n is smaller than 1. It is smaller than s divided by n to the s plus 1, because t is at least n. So this is bounded by the integral of s by n to the s plus 1 dx, which is the integral goes away, which is s by n to the s plus 1. So you get a bound, and the nth term is, what you see is that this has an extra plus 1, right, because of the derivative. And that's what makes this fine for all s positive. Hence, the right-hand side, so this right-hand side, if you call this, so if you, to be strict, what we are saying is that if Gn of x is n to n plus 1, 1 by n to the s minus 1 by x to the s, yeah, Gn of s, not x, Gn of s. If this is the case, then what we are saying is Gn of s is bounded by s by n to the s plus 1. Hence, this is a uniform, yeah, it's not uniform, it's a bound. Hence, summation Gn converges for s in 0 to infinity and uniformly for s in delta to infinity for all delta positive. Okay, so 1 by n to the s plus 1 will converge like that. So this is that's the proof. So this thing is this is what I call zeta tilde of s. I mean, it's not any important notation. So this is the zeta tilde. But the point is the convergence is of the order like 1 over s minus 1. That's how it blows up. Zeta function, actually one of the things which we are not going to do here, we could do with a little bit extra trouble, that's all. And it's something that Dirichlet did not do and Riemann did, is to take S to be also a complex number. That was one of the great innovations that Riemann used, that he extended S to be a complex number. And then, in fact, this converges for all S, not just on 1 to infinity, but to the right of this half plane on 1 to infinity, with real part S bigger than 1. and it defines a holomorphic function there and blah, blah, blah. All those, that's very important, but not for this problem. Dirichlet was the one who first used these things, and Riemann used this for extended it to the complex plane and found many properties of it. So in that language, zeta is said to have a simple pole at 1. If you know that language of complex analysis, zeta has a simple pole at 1. Okay, anyway, this takes care of 1 by n to the s. So let's go to the next thing. What next? So from that, of course, if you have anything with bounded coefficients, if ANs are bounded, so here I even allow ANs to be complex numbers. Summation AN by n to the s, n equals 1 through infinity, converges absolutely for s in 1 to infinity, and the convergence is uniform for s in 0 to infinity. Sorry, for s in 1 plus delta 2. Okay, so this is obvious. I mean, you just put the absolute value, no problem. But there is no guarantee that this will diverge as at s equal to 1. In fact, we'll see now that it need not diverge. It depends on the kind of numbers you take. If you take positive numbers, okay, even then if ANs have decay, then it of course doesn't. So let's go to the next one. So this we have analyzed the zeta function now. Okay, so now let's come to things. So in fact, sometimes the convergence can be better. Okay, the convergence can be better. What is an example? So here is an example. So if you take something like minus 1 to the n by n to the s, let me make it minus 1. So this is 1 minus 1 by 2 to the s plus 1 by 3 to the s minus 1 by 4 to the s plus and so on. Okay, so this actually converges for all s positive. Okay, it doesn't only converge for s. If you want absolutely, then it converges. Then you put absolute value, it becomes zeta function. Then it converges for s bigger than 1. But with the signs, it converges for s positive. There are many ways to see it. One way is that you see this is an alternating series. The signs are alternating and the terms are decreasing. So there is something you see in usually given in first calculus course that such things converge. That's not convenient for me. So let me give a different argument. I mean, so which you know also that because this I'm going to put complex numbers, then this decreasing business doesn't make sense. So the way to do it is you combine these terms in twos. So if you look at 1 by 2n minus 1 to the power s minus 1 by 2n to the power s. Okay. So exactly like here, 1 by n to the s minus 1 by x to the s, I got like this. So you can write this as, so this, let me just write, it is of the form s by t to the s into the difference. The difference in this case is 2n and 2n minus 1, that is 1. So this is actually in fact less than equal to s by 2n minus 1 to the power s, right? Exactly by, by s plus 1, s plus 1. So this is from exactly the same reasoning, okay? So, I mean, exactly this 1 by n to the s minus 1 by x to the s, we got like this. So here it is 1 by 2n minus 1 to the power s minus 1 by 2n to the power s. So it is of the order of one. Basically, you think it is 1 by n to the s plus 1. Hence, and summation 1 by 2n minus 1 s plus 1 is finite. So that converges. So that's why this thing converges. So this is the what is happening is that there is cancellation happening because of these oscillatory terms. Now instead of 1 by minus 1 minus 1 plus 1 and so on, what happens if you, so you can similarly reason. If you take something like let's take a cube root of unity and consider such things. So this is a cube root of unity to the power n. So this, you see, it oscillates between three terms. One that usually denoted omega, omega square, right? So it keeps oscillating 1 omega, omega square, 1 omega. Instead of 1 minus 1, it is oscillating between three things, but their sum is 0. Because of that, what you can do is you can group terms by threes. Okay, 1, 2, 3, 4, 5, 6, and so on, and similarly show that this converges for all s positive. In fact, so that's what I want to prove in a very general way, a very simple lemma, which will take care of convergence issues. We don't even need that exact periodicity and all that. So here is a lemma that assume that, okay, ANs are here complex numbers and partial sums let's call it an equal to k equals 1 up to n ak are bounded. So earlier I assumed that the terms are bounded, but here I'm assuming that the partial sums are bounded. Okay, so then this converges for S positive and uniformly for S bigger than delta. Any delta positive. Okay, I did not write converges absolutely. It is not true. Here the crucial point is the cancellation of AKs. That's why it can stay bounded. If AKs, I mean, so the reason it can stay bounded, okay, either AK can decay rapidly, in which case, of course, that will itself give you the convergence, right? If summation AK itself is finite, then even without the 1 by S into the S term, that will converge. That is not the interesting part. Here, AKs are not, the interesting part, as we'll see, is not AKs going to 0, but AKs stay like maybe of absolute value 1, but they are oscillatory and their cancellation is what causes this convergence. Okay. So, well, proof is easy. Wow. How do you prove it actually? So if you haven't seen this, it's similar to, I mean, you may want to group, but there is no exact cancellation here. Okay, so it's not, it's one has to be a little more subtle about it. You cannot group terms to cancel them, but we'll just directly check the Cauchy condition. Okay, by Cauchy criterion, so for what we need is for epsilon positive need some n epsilon integer such that if you take the partial sums, let's call it ak by k to the s or an by n to the s. If you take the partial sums, n equals k to l, that absolute value of the partial sum should be smaller than epsilon for all k L bigger than equal to k bigger than equal to this n epsilon. So that's what we need to find, right? So you just need to show that these partial sums are uniformly bounded. And that is, so how do you handle that? So fix such a k and l. So fix, so look at, I mean, fix n equals, consider this n equals k to l. an by n to the power s. How am I going to make use of the cancellation of ans? This is a very useful thing to keep in mind, both in discrete and continuous. You have an oscillatory term and you have this is not oscillatory. 1 by n to the s is not oscillatory, but it is always positive. It has a decay, but you are combining it with an oscillatory term and you want to get faster convergence, right? Or more convergence. So a very good idea in that is always to take integrate by parts in such situations. So here what we do is summation by parts. So let me explain. So you just do summation by parts. So what is an? An we write as capital An minus capital A n minus 1. So we write it as the difference of its cumulative sums. And now regroup the terms so that we write. So what does an come with? An comes with 1 by n to the s minus 1 by n plus 1 to the s. Most ans, okay, so I will worry about the boundary terms in a moment, but n which is not at the edge, it will come with 1 by n to the s, and it will also come in 1 by n plus 1 to the s, but with a negative sign. So this is what we get. So this works for, okay, what are the terms remaining? Which ones don't come like that? So this is okay for n equals k up to L minus 1, I guess. N equals k up to L minus 1, it's okay. But then there are two terms which are AL. AL doesn't come with L plus 1 to the s, so AL by L to the s. And in the n equal to k, we also have a k minus 1. So this is called summation by parts. It's exactly like integration by parts, and this is the standard trick to use the oscillatory nature of one of the integrands. Okay, if you have a product of two integrands, one is oscillatory, the other is not. This is how one way to exploit it. Now, what of it? So absolute value of this we can now bound. We know that ans are bounded, right? So we know absolute values of ans are bounded by m for some m and for all m. So therefore, if we look at put the absolute values now, an by n to the power s, what can I bound it by? I can put the absolute value here. I put the absolute value here. So I get, so when I put the absolute value here, I can pull the m out and I am left with 1 by n to the s minus 1 by, since that is anyway positive, the absolute value is not needed. Plus this is bounded by m over L to the s, and this is bounded by, okay, this is anyway, yeah, okay, so m over k minus 1 to the power s. So the whole thing is, so this is a telescoping sum, so we get, this will give me 1 by k to the power s. So this is actually 1 by k to the power s minus 1 by L to the power s, right? So that's what we get, plus this term, which is, let's just write m times 2 over k minus 1 to the s, or 4 by. There are 4 terms. In all of them, there are 4 terms in all of them. Anyway, yeah, so let's. The denominator is at least k minus 1, so we'll write this. So from this, you see that if s is positive, you can make it small, right? So if s is positive, then, so for s positive, or for s bigger than positive, choose k n epsilon such that OM by n epsilon minus 1 to the power s is smaller than epsilon. So that's the trick. Okay, I went over it in detail. There is only one idea, namely the summation by parts idea, to utilize the oscillatory nature of the. Okay. Any questions, comments, or anything?
Sir,
Huh.
the first step, summation n equal to k to l an by n to the s.
Yes.
So from there, can't we just pull out 1 by l to the s outside, and then summation an that is just bounded by 2m? So
No. They are oscillatory, right? So you cannot pull out a term like that. I mean, you cannot say. So they don't have the same sign.
ans don't have, but n to the s are all positive.
Yes,
Right?
but that doesn't mean. So what you are saying is that. I mean, so something like, I mean, so you want to pull out the maximum term, but that is not true if the signs are different. I mean, you can just try with whatever you want. I mean, so the whole thing, for example, I mean, it's so because the signs are there, that such a thing is not true. So you want to write like this. Such a thing is false. So let's take an example here so for example, take something like this, right? So just take an example here. So you are trying to say 1 minus 2 to the s is bounded by 1 by 2 to the s into 1 minus 1. Right? Here an is, that's not true. This is 0. This is not 0. This is positive. So when you have positive, when you have, yeah, you can pull it out, then you have to put absolute value on the remaining things. But if I put absolute value on an, then I have no assumptions. In fact, that will not be good for me. If I assume what you are saying will work, if I assume summation mod ak will be bounded, but that is not what I want to assume.
Yeah, that's why we need this summation.
Yeah, exactly. Yes, you need something like this. You have to do this. You have to use the sums.
Thank you.
Okay. Any other questions?
Shouldn't there be k to the power s?
Yes.
Bound k is the.
Yeah. So this is k minus 1. I got.
Oh, that's k minus 1. Okay.
Yeah. Sorry. I mean, when I was writing, it was clear. Afterwards, it doesn't look like k minus 1. So here there were 4 terms, 1 by k to the s, 1 by l to the s, 1 by l to the s, 1 by k minus 1 to the s. I just bounded all of them by 1 by k minus 1 to the s.
I think that will get cancelled 2 terms, right?
Yeah. Actually, yeah, you can. There is also a negative actually, but I just extravagantly I left it as 4 terms. Yeah, there are 3 terms actually. If I put absolute, yeah, even here I could have dropped anyway. So I did not care about saving there. So it is something like this. Yeah, you're right. So this takes care this because of this. So now let's come to what are so L functions. Now let's come to L functions. Fix D, I mean greater than equal to 2, and chi character of chi. Okay, character of ZD star. Okay. So and remember the Dirichlet L function. L chi of S is defined as summation chi of n over n to the power s. N equals 1 through infinity. Okay, so this is S. Okay. So you may remember that chi of n is now defined for all integers. Chi of n is defined as chi of n bar, where n bar is the n mod d. If n is coprime to d. Otherwise, it is not in that group, right? To fall in ZD star, it has to be coprime to D, and we have defined it to be 0 otherwise. So the point is Dirichlet L function. The when for what S will this converge? So there are two cases. So if chi is not the trivial function, so first let's take the non-trivial case. If chi is not equal to the trivial character, then the partial sums are bounded. Why? I mean, because if you look at any, so you take any d consecutive numbers. Okay, so let's take. So let me say this: chi of n partial sums are bounded. Hence, L chi converges for S in 0 to infinity, and it's in fact uniform on delta to infinity. So it is. So it's a continuous function. On 0 infinity. It's a continuous function on 0 infinity. And so the only thing I need to justify to you why these are bounded. I mean, this is easy because they are basically, they cancel actually. So this is because you can sum over any consecutive D numbers. Okay. So if you sum over anything, actually n equals any k to, let's take multiples of D. Okay. So let's take k times D plus 1 to k plus 1 times D, chi of n. So here every residue class will occur exactly once, right? And all these zeros are there. Those that are not coprime to D, they will give zeros. The remaining, because we are taking D consecutive numbers, each residue class, I mean, all these will come exactly once. So this is actually same as. So there is a slight abuse of notation. I use chi for the function on natural numbers as well as on the ZD star, but it's okay, I guess. So it is sum over x in ZD star of chi of x, which is same as chi inner product, the trivial character, right? In L2 of ZD star. So that is 0 always, because these are two characters. This is trivial character, and this is a non-trivial character. So the inner product is going to be 0 because we know that characters are orthogonal to each other in the L2 of the group. Therefore, we get this is 0. So now you see that they are summing to 0, like in this situation. Here you can group in 2 and they add to 0. Here you can group in D's and then they add to 0. So that's how you get this is actually 0. And hence the partial sums are obviously bounded. I mean, in between they are not 0. So if you add something, you have first D partial sums and then they keep repeating again from this. So are bounded. Okay, so they are bounded. So for any non-trivial character, this convergence of the L function in us is on 0 infinity, not on 1 infinity. Okay. What about the trivial character? Okay, if L is the trivial character, then so let's say let's call chi is 1. Okay, so one should be slightly cautious here. So I'll write like this, L1 of, or maybe I call it chi naught. So chi naught will for me denote the trivial character. L chi naught of S is, so the thing is, it's not the same as zeta function for a small point, that it is actually 0 when n is not coprime to d. So that's why I didn't want to write 1. You might think it's 1 by n to the s, but it's not. It's 1 by n to the s, yes, but only over n which are coprime to d. Other things don't contribute. They are 0. Well, you're summing over a bit less than the zeta function. Will this make a big difference or not? Okay, so it won't make much of a difference because, so one, on the one hand, this is clear that it is less than equal to zeta s, right? On the other hand, this is also greater than equal to. So what are the things that are not coprime to d? Okay, so let P1 up to Pk be the distinct prime factors of okay. So then if it's so, I can write it as sum over n such that n is not coprime to d. What does n is not coprime to d means? N is divisible by one of these. Okay, so this part is actually equals. So that means n has to be divisible by one of these primes. It can be divisible by more than one. So I'll write an inequality that it is, I will take 1 by n to the, so let's take multiples of P1. So that means k times P1 to the power s. K equals 1 through infinity. All multiples of P1. Sorry, k is not a good one. So maybe I call this P1 up to Pm. P1 up to Pm. So and so on, minus k equals 1 up to infinity. 1 by kp2 to the power s. Minus dot dot dot. There are m of them. So some terms occur in multiples ones of these. That's why this is not equal but unequal. So P1, P2 occurs here as well as here, whereas it should be subtracted only once. So, well, you can do an inclusion exclusion if you want. In fact, we'll find exactly how this is related to zeta function. You can do an inclusion. If you do an inclusion exclusion, you will get an actual relationship identity of L as a multiple of zeta with something. Okay, but I don't want to do that. At the moment we will do that. So but this is actually what it is, zeta of s. If you pull out 1 by p to the s, what you are left with is zeta of s. So it is 1 minus 1 by p1 to the s minus 1 by p2 to the s minus dot 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 minus 1 by p m to the power s. Actually maybe then this is a problem, because is this positive? If I bound it like this, yeah, so there is no guarantee that this sum is less than 1, right? In fact, if I take s close to 1, I can make this larger than 1. So this is actually, I have to do the full inclusion exclusion, I think. Yeah, do you see the problem? I mean, I wanted to say, okay, so the convergence, what I wanted to say was, if you allow me here, then L is on the one side bounded by zeta and the other side bounded by zeta times a positive, I mean, something that depends on s, but I want to say this is positive, okay? If that was the case, then we have the clear understanding of how L diverges. It also diverges, zeta diverges like 1 over s minus 1 near s equal to 1. So same thing for here. But there is a slight issue here that this need not be positive, because when S is close to 1, this sum can be large, right? So sum of reciprocals of these will be large. That's what I mean. We'll show that. In fact, that is true. That is what I said when I discussed Euler's theorem. But so this is not a good way. So I have to do a full inclusion exclusion here, I guess. Okay, so maybe I don't know if I can get it right here. So can somebody see a way out? I just want to say L converges for S positive, S bigger than 1. Yeah, so from here it is clear it converges for S bigger than 1. That is okay.
So I might be wrong, but if you do the inclusion exclusion, I think all you will get is zeta S times 1 minus 1 by P1 times 1 minus 1 by P2, those kinds of things.
With the S, 1 minus 1 by P1.
Yeah, with the S. So that's
that's exactly what you get. So converges absolutely for S bigger than 1. Okay. So yeah, so it's exactly like Abhishek said. So you just do inclusion exclusion. So then here we will have to take over K times anything that is a multiple of 2 of the primes. We add up, right? So this is an inclusion exclusion. Here I take sum over K, but over I less than J. I mean, so something like this. And then there is a minus with where something is a multiple of 3 primes. I1 less than I2 less than I3. Sum over K, 1 over K times Pi1, Pi2, Pi3 power S plus dot dot dot. So this is the inclusion exclusion. So, well, I will cut short like Abhishek said. If you do this, what you get is actually zeta of S into product of 1 minus 1 over Pj to the power S, J equals 1 up to M. All these excluded primes, I mean all the primes that are divisors of D, you will get their product. So you kind of see, right? I mean, in each of these, you get zeta S actually. All this is zeta S over P1 to the S, zeta S over P2 to the S. This is zeta S over P1, P2 to the S. So you pull out zeta S. What remains is 1 minus summation Pi. Yeah, so this is actually, I can even write. So this is, if you pull out the zeta S, you will get 1 minus sum over I, 1 over Pi to the S. I goes from 1 to M only. And then you will get a sum over I less than J Pi 1 over Pi Pj to the power S minus and so on. So that is exactly this product, right? So that is gives you this. So you get this formula.
And that's an equality now. We don't need any inequality.
Yeah, now it's actually, yeah, thanks. This is not inequality. This is actually equality. So this is actually a useful one that we have found. So we have found that L, the trivial character, L chi naught of S is actually zeta of S times product J equals 1 up to M, 1 minus 1 by Pj to the power S. Okay. So next, so what I am going to go into next is the product formulas. But here is already one hint, small hint. If zeta, if you accept that zeta has that Euler product formula, product over all primes. So if you remember Euler product formula, this one. Where did it go? So zeta S is product over P 1 over 1 minus 1 over P to the S. So for the trivial character, all those primes which divide D will be cancelled. So it will still have a product form over primes which don't divide D. Okay, so that's a hint of things to come. We will now prove the product formula, which I have already indicated last time, but without the rigor of convergence. That's all. Last time we indicated that whenever we have a completely multiplicative function, we have a product formula. Right? So when an is completely multiplicative, where did I write this? Huh. So yeah, I even remarked this. Chi is completely multiplicative. Therefore, summation chi n over n to the s should be this product. But at that point, I was not careful about convergence. And also question is for what s does it work actually? Okay, that should be give us a bit of caution that in fact, we know that if it's a non-trivial character, this side converges for s positive. Is the product formula valid for s positive or for s bigger than 1? Okay, so this is the next point that I will go to. So the product. So we have investigated the L functions from just the series form and their convergence. Okay, so from here we see one point that we see is in fact that the divergence as a corollary. From this we see that L chi naught of S. There is this formula is like up to a. So when I write like this. So, okay, by the way, these things have precise meaning. If I haven't said it before, let me say here. When I write, whether it's a function an, bn, or a function gx, means that there is universal constants for some c. Or for the function, okay? That's what I mean when I write this this symbol. This symbol is for.
So Manju, just a small point. I mean, here with the inclusion exclusion, it is clear. But
Yeah.
if you only want weaker, I am wondering whether that second you subtracted off the sum where n comma d bigger than 1, right?
This one, yeah.
Yeah, but there I wonder whether one can just write suppose n comma d is equal to t. T is a divisor of d. Then n by t and d by t are co-prime. I wonder whether one can just divide by t and then write the sum in a different.
I see. Okay, okay. Yeah, you may be right. Actually, that may be true. I see. So
because
here,
I think that will you will get then you will just be summing over. So if n comma d is t, then n by t and d by t are co-prime. You just multiply and divide by t in that sum. So you write as n by t power s and times t power s. Then you can probably pull out. So I mean it is just weaker, but you have got the full strength anyway. You have written the full product formula.
No, you are right. Actually, that may be nice. So that side, this term becomes again the L function, if I'm not mistaken, because you will get sum over coprime things, right? N by t is coprime to d by t.
D by t, yeah.
So not to d. I see. So then, okay.
Okay, I don't know. I just thought that maybe that might give something.
It is quite possible that, I mean, there should be a way to, subtract a bit less. This is a bit overkill, just the way union bound always doesn't work. So something is, we have subtracted too much. But what you are saying is a good way also, maybe. I haven't tried that way. Yeah.
Okay, just a minor remark. Yeah, anyway.
So someone can maybe try it and let me know if it works. I'll also think later. Any other questions, comments? So here we are not saying it is like, so zeta function, by the way, I'll introduce another notation, also already introduced, the wiggle. So when we write an wiggle bn or fx wiggle gx, usually we have to say as n goes to infinity, as x goes to infinity or 0 or something, means the ratio goes to 1. Or ratio goes to 1. It's an asymptotic relation. So for zeta, we have the stronger thing. So for zeta function itself, it is 1 over s minus 1 because zeta is actually, we saw zeta function is actually 1 over s minus 1 plus something that stays bounded. In fact, the difference is bounded. So the ratio of zeta s to 1 over s minus 1 will go to 1. Because you divide by 1 over s minus 1, this will bound it, so that goes to 0. So that for general trivial L function, it's not quite that because there is this. Actually, what happens to this as s goes down to 1. actually, so you'll get, you can figure out the constant. In fact, L chi naught of S will be, so if you want to write in that way, L chi naught of S is actually, this one also stays bounded as S goes to 1. So this, if you want to write with a wiggle, it is product 1 minus 1 over P over primes that divide D. Okay, this is a notation for P divides D. I had not used it before. I could have written Pj, but anyway, so is this over primes that divide D, this, because that's what happens to this as S goes to 1. So you get this formula. Okay, that's it. So next, let me go to the product formulas. At a, slightly non-rigorous level, we have already seen it. Now let's do it properly. So let's prove this lemma that I had said last time, that if A is completely multiplicative, where did I say it? If A is completely multiplicative, this maybe I write it since I haven't written it. So let's write the lemma. A is a function from natural numbers to complex numbers. Is, let me assume it is bounded and completely multiplicative. We will apply it to characters which are bounded anyway. Then the sum is equal to product product over primes of 1 over 1 minus AP by P to the power S. Okay, so this is what for S bigger than 1. In the fullest generality, it is for just S bigger than 1. When the partial sums are also bounded, we want to extend it to S bigger than 0. When the partial sums of A are bounded, the left side is fine for S positive. Then we want to also say this is also fine. But first, let's do it for this. So this is actually, there is nothing very subtle in the proof actually. Whatever we gave was more or less okay, except you maybe take, so order the primes. P1, P2, P3 and so on. So first let's take the, product. Let's take a finite product. J equals 1 up to K, 1 over 1 minus. Okay, I got AP. Okay, since I got as function, I could also have written A of P, but okay, for whatever reason, I got it as subscript. AP by P to the S. First of all, each one can be expanded by as 1 plus AP by P to the S plus AP. You can write it as AP or AP squared. AP whole squared or AP squared. Both are the same. This is valid for any S positive. Okay, so because P to the S, 1 by P to the S is, yeah, okay, that's it. So this is because I'm using, yeah, anyway, this is okay. But when we multiply this, so now the claim is this. So this is the claim that I want to say, that n equals, so n in natural numbers, all natural numbers, such that n, all prime factors of n are in P1 up to Pk. in P1 up to Pk of 1 by n, no, sorry, an by n to the power s. So this is okay. Is this okay or not? So this is for s bigger than 1. Okay, so this is more or less okay. I think I will not maybe try to justify. I mean, the justification is not. So what is the problem? When s is bigger than 1, this is absolutely convergent actually. Okay. When s is bigger than 1, this is absolutely convergent. And if you multiply this out, you will get exactly these things, right? You will get the primes. What you get in this product, you will get, I mean, exactly this kind of stuff. And then we are using the multiplicativity. So maybe I just, oh, okay, I'm almost out of time. So this will give me sum over all exponents E1 up to Ek of greater than equal to 0 of AP1 to the E1 dot 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 APK to the EK.
It's 1 o'clock.
Divided by P1 to the E1. So when we expanded it formally, this is what we got, right? And so this gives you a 1 over n to the s and an over n to the s over all n's like this. The only point is the rearrangement, which is justified. I mean, you can, since it's absolutely convergent. So it is okay. You can you can rearrange in any way and it is fine. Okay, so this part is okay. Now let okay, I'm out of time. So but let me just write. Now let k go to infinity. Okay, I let me complete it next time. Okay, so rather than try to rush it. It's not, I mean, when k goes to infinity, here you get the infinite product. Here you get the restrictions become smaller and smaller and you get over all n. There's nothing subtle as far as I can see. Okay.
So, sorry, just what was assumed on the ends? Just can you go back to?
Multiplicative and bounded. I assume bounded. So you get absolute convergence of this for s bigger than 1. And completely multiplicative is where I'm.
Yeah. Okay, thanks.